Now let's start with our today's second session, and co-founder and CTO of FLEXOPTIX GmbH, Thomas Weible, and his presentation title is Analyzing Network Reliability up to 800G, Impact of SNR. The stage is yours.
Thank you very much, Cornelia. Hi. My name is Thomas Weible, co-founder and CTO, as Cornelia already mentioned, of FLEXOPTIX, a company which is 99% specialized in optical transceivers. And today, my topic is, actually it's quite funny because Ben had in the morning, in the first session, a talk about what kind of weird things you can with transceivers. We took it on a different approach to look what we can do when we do analysis with transceivers in your live network or even before you deploy a link. Because I assume when you deploy your link and run them, you monitor them quite well, especially the 5 well-known values like temperature, TX and RX levels, and also the bias current going through the transceiver and the voltage. Now, there is, with latest technology, up to 800 gig, there will be more metrics available, and I want to show you a little bit what we actually can do there. And for that, the presentation is a little bit separated in 2 sections. We did in our own lab some analysis, also when we go to longer reaches or longer distances, or basically to the edge cases. And then I will also add a live demo to show you how it's actually working in a prototype environment currently, which we have developed. But first of all, we have to go a little bit back in history, back to 6 years ago, when the first 400 gig transceivers were introduced in a nice form factor as a pluggable, like QSFP-DD and OSFP for the transceivers. When we look at the schematic of a transceiver in general, you have 2 different type of sections. You have either the electrical side, and typically when they were developed, the 400 gig transceivers, the design was, okay, we run 8 parallel lanes out of your switcher router from the ASIC to the transceiver, and each lane is carrying 50 gigabit. And then on the optical side, the optical engine was typically, when we look into single mode application, 4 times 100 gigabit. Now, you need to do some conversion, doing 8 times 50 gigabit to 4 times 100 gigabit, and there is this purple gearbox there involved. So basically it's a multiplex on the electrical side, combine 2 lanes to 1. That's the rough idea. So yeah. Also back in 2019, when those form factor came up, and this here you see a picture of a QSFP-DD. When we open it up, there are a couple of components in there, 4 major ones. So the 2 golden boxes you see there, this is the transmitter and the receiver, or we call this the transmit optical subassembly, because there are quite a lot of components inside. And also on the receiver side, on the lower part. And then when we look on the PCB side, there are 2 chips. The smaller one is the microcontroller doing all the management information, controlling the transceiver and also reporting backwards to the host. And there is this big block, or this big chip. It's a digital signal processor. In general, this digital signal processor has a couple of functions. It takes care about modulation. When it comes to coherent, there's even more work to do for the DSP when it comes to the modulation, talking about 16 QAM modulation, for example. And also this digital signal processor has the great capability to do a forward error correction. So it can correct errors on your line when you receive them, and can also do analysis and measurement. So the DSP, when you set it into a certain mode, it can generate bit patterns and also checks those bit patterns if they have, and is very important, on line rate. It can generate it on line rate and check those bit patterns if they are matched and aligned to each other. And if not, then the error counter will go up. Beside that, we can even measure the signal to noise ratio, either on the optical side, which is the OSNR, or on the electrical one, which is the ESNR. And especially now in this talk, we focus on the bit error rate and the SNR, and yeah, part of the DSP. So what did we do? So we basically took invention and development. What we did is the Flexbox. It's a tiny USB device, and even these days it can even do Bluetooth and so on to connect to your computer or to your smartphone. And it does the conversion to the transceiver itself, to the management interface, that you can for sure power it up and also control the transceiver. So we took that Flexbox and a couple of transceivers. When we focus in the middle, these are the typical 400 gig transceivers, either a coherent one or even an LR4, or latest developments are a QSFP 112, which is basically, instead of having 8 lanes running on a speed of 50 gigabit, going down to 4 lanes running 100 gigabit on the electrical side. And an interesting side effect of the 400 gigabit development with the DSP inside of the transceiver now is we were able to build also 100 gigabit transceivers driving one lambda, one single wavelength out of that transceiver. And so, yeah, this is based on the QSFP 28 form factor. And here we were looking at a short distance, 500 meters, and or even a long distance one, 40 kilometers. And finally, we took an 800 gig transceiver running 8 parallel lanes, doing 100 gigabit, mainly for data center applications. So we tested them all through, and I don't show all the results now because this would extend this presentation pretty much, but I will show a little bit what we figured out there, especially on the edge cases. The lab setup was pretty straightforward. So we took that Flexbox, plugged in the transceiver, and for some types, especially the coherent plugs, we needed a cooling capability. We needed a heatsink and also a fan, which we attached to it. Interesting one here is that actually we took this heatsink out of an old Cisco 800 router, and those routers were released roughly 25 years ago. So latest development on 400 gig coherent met somehow 25-year-old technology. A good friend of mine, he decommissions equipment in Frankfurt area, so we are based in Germany, and he rips out the components, separates the different materials, and then recycles them for various reasons. So if you ever face issues in Frankfurt, let me know. He's really good in that, separating all kind of gear. And he gave me a couple of heatsinks to play around in our lab. Okay, now, how did our setup also look like on the fiber side? The fiber side, first of all, we have chosen the transceiver. Now here, this is the 100 gig ER4 running 40 kilometers maximum. We took a couple of fiber drums, typically 10 kilometers has each fiber drum, and we cascaded them for 10 kilometers, 20 kilometers, and so on. And then we looped the transmitter to the RX side, to the receiver side, and we also had to add some attenuators there because we wanted to look at edge cases. So when we look at the red rectangle, especially on the receiver's minimum, which is minus 14 dBm, actually that's where we wanted to look at what's going to happen when we are close to that value for various distances on the fiber span. And for sure, on the shorter fiber spans, like the back-to-back one with 2 meters, we also had to add attenuation to protect the receiver, because otherwise, when you look at the minimum or even the maximum transmit power per lane, it would overload the receiver, because this is rated up to minus 3 dBm, so we had to add some attenuators there. Okay, so, and then we run the bit generator out of the DSP, checked for the patterns, and measured the bit error rate in general. And what did we find there is on the y-axis, on the x-axis, sorry, we do have the temperature while it's operating, and on the y-axis it's the bit error rate, typically counted in exponents, so 10 to the power of minus 5, minus 4, and the smaller the exponent, the weaker our signal is, or the more errors we have in that signal. So the goal is always to have a big exponent number, and there is a demarcation line, the 2.4 multiplied by 10 to the power of minus 4, and that's basically a definition by IEEE where it says, okay, this is the minimum or the maximum of bit errors you you should achieve, because otherwise your forward error correction won't be capable to correct those errors any longer. And then the errors will be handed over from, let's say, layer 1, layer 1.5 to layer 2, and you will encounter framing errors on layer 2. And yeah, on the distances itself, the 10 kilometer look good, the 30 kilometer look good, and even the 40 kilometer look quite nice. And interestingly is the 20 kilometer one. It was really operating close to the edge of the 2.4 multiplied by 10 to the power of -4 bit error rate. And we wanted to know why. So we looked also on the RX power, and there we saw, okay, actually we hit the receiver's minimum quite precisely. Actually, we were really at the edge there at -13.4 dBm. And this is, I think, a really nice comparison where you can see that the receive power actually has an influence on the bit error rate you generate, or what happens when the transceiver is operating. You might wonder about those tiny glitches which you see. They are always dropping the bit error rate, where we highlighted them with the red circle with the question mark. That's actually when the transceiver itself, while it's operating and while it's heating up, it does a correction on the TX, on the transmitter's bias going through the laser. And we can see these are drops, so it's always increasing the bit error rate. So the signal is getting a little bit better and reducing the amount of errors. Okay. Then a little bit about theory on the bit error rate in general. So what is this bit error rate? It's a pretty simple formula. So when you look there, the amount of errors, and they are typically clustered, let's say 100 errors, and you divide this by the total amount of bits you transmitted in a certain period of time. That's the whole mathematics, which is done to get those bit error rate figures. Now, when you assume you have 100 errors on a 100 gigabit link, and you want a really almost bit error rate free link running at 10 to the power of -12, which is pretty good, this gives a gating time of those clusters of error clusters of roughly 16 minutes. So every 16 minutes, such an error cluster will occur and needs to be taken care about the forward error correction. So that's a pretty long time. Now, when we shrink it down and the bit error rate gets worse, down to -4, and looking at this limit, which I showed previously, the 2.4 multiplied by 10 to the power of -4, the gating time really shrinks down to 4 microseconds. So there are a lot of errors on that link, and all of those errors need to be taken care of by the forward error correction. So the worse your bit error rate gets, the more the forward error correction has to correct actually. Beside the distance, we also wanted to see, hey, what's going to happen on the temperature side? Because also everyone knows temperature is a critical thing, otherwise you wouldn't cool your equipment in typical data center environments. So our thing was, hey, what's going to happen when we go over spec? The typical spec is 0 till 70 degrees of operating temperature for commercial environment, and for industrial it's plus 85. But what's going to happen when we go beyond 85, even up to 100 or 120 degrees? My colleague Gerhard, he plays a little bit around and he likes it quite well. He used his barbecue, placed the Flexbox there, covered it with alloy foil because he wanted not the heat getting into the electronics of the Flexbox itself, placed the transceiver inside, and then he basically used a heat gun just to heat up everything to get to those high temperature. For sure, he was only able to inject the heat from the outside. And this really matters because when we look, when we were operating the bit error rate, we also see there a correlation that the hotter it gets, the more errors will occur, all still within specification. But then at a certain point, diagnostic also kicked in and said, hey, there's a high temperature warning at roughly 72 degrees. And 3 degrees later at 75, 76 degrees, we hit also the high alarm when we heated it up. And then an interesting thing happened at roughly 80 degrees centigrade. It stopped working, but it was not the transceiver itself, it was more the loss event. So the transceiver shut it down, the transmitter, and then, yeah, the link was basically down, and that's actually the point where you, as a network engineer, start to look at your link because no traffic is passing that link any longer. And we figured out, hey, that's a safety protection out of the DSP. So the DSP got too hot, and then it decided, okay, I'm going to stop operating, basically to protect the electronics itself. When we cooled it down again, everything was back to normal, the link was coming up again, and everything was fine. But this was an interesting finding, so we were not able to break it. That's basically it. Before I'm going to start now the live demo, there's another measurement which I already mentioned at the beginning about the signal-to-noise ratio. Because the signal-to-noise ratio is quite new to datacom people when you operate a network. It was in the past mainly intended for people running DWDM networks, or transmission folks. So what is the signal-to-noise ratio? Quite simple and straightforward. It's the ratio between the desired signal and the noise level on the overall link itself. And the goal is to have a big gap between the desired signal and the noise level. So here on the graph you see, we measure it in decibel. It's at 25 dB, which is perfect. So the range should be between 20, not below 20, because then the noise goes way too high or closer to the desired signal, and then it's way harder and even not possible any longer for the receiver to distinguish, hey, is this now a noise or is this my desired signal? Yeah, so not below 20 dB. And an analog example is basically like here giving that talk. I mean, I got here perfect audio coming out of the audio system, and you guys are quite quiet, so the signal-to-noise ratio is perfect. If I would do the same talk in a cheering football stadium, it would be way harder to distinguish between what I'm saying, not taking consideration about the content, but what I was saying, and then the stadium is quite loud, so the SNR would be very bad there. Okay. Here we go. So let's have a look how this actually works and is in a live environment. So what I'm doing now, I got here a 100 gig transceiver, looped with 2 meters of jumper cable, connected to that device, holding it, the Flexbox, and I got it connected via USB. And I have to run my script. So what we do see here is we pull out 4 different values. The obvious one is for sure the temperature again, and we look at the RX power, and then we measure them on the media side. So on the fiber side, we measure the bit error rate, and also then later on the signal-to-noise ratio. It takes a little bit to set up everything because we have to power it up and then boot up the DSP, bring it into the checker and pattern generating mode, and now it's writing the first patterns. It's using the pattern, the PRBS 31. It's a well-known pattern generator, and we have to give him a little bit time to settle down because we only have some values at the moment, and we get some nice curves. Right, so the link is perfectly fine. We run at a nice BER of -11, and the RX power is at +1.7, which is perfectly fine. And you also see the temperatures going up, but all within the range now. And now I'm going to simulate a dodgy fiber or a broken fiber or even a long span. And when I add now attenuation, and I can do this quite simply to bend it a little bit, and you see it on the RX power, we're going down now. And the more I add attenuation, you see the BER is going up and up and up. It's still fine. And we can even now try to hit the receiver's minimum. And it's not that easy. You can later on play as well if you want to. Please don't break it. It's lasting for a while now. So, but yeah, it's quite obvious, there is direct influence on the bit errors generated, the more attenuation we have. And when we're going now below the receiver's minimum, we are going basically through the rooftop and we are at 0. This is a link loss event basically, so there's nothing going through any longer. And yeah, although we still see some light, and I bend it quite hard at the moment, yeah. When I release it again, RX power will be fine. The BR will recover now, but interestingly is also when you look at the figures now, it doesn't recover instantly because it's a rolling average. It's statistically, so we do have some errors in the past already measured, and when we do the overall calculation, the bit error rate needs some time to recover to proper values back. So we are getting better now at -3, and it will jump later on to -4 and so on. If I'm going to enable now also the SNR, you will identify another thing. It's slowing down a little bit because this bus, which is used to communicate with the microcontroller, has some limits, especially in bandwidth. And we are basically hammering on that bus quite heavily, but now we have to access way more memory, and due to this fact, it's slowing down the overall process because beside the BER, we are also gathering out the SNR values now. And yeah, we are 23 dB, perfectly fine for the signal-to-noise ratio, and pretty much the same you will see on the SNR side. So when I add again attenuation there, and it's a little bit more difficult now because it's a little bit lagging, you will see the SNR will drop, and we are getting a weaker signal, and then at a certain point, at roughly 20 dB, yeah, the SNR is gone. It jumps up to 30 dB. This is similar like the -40 dBm when you have RX loss. So there is another effect kicking in. So our goal is having an SNR between 20 and 30. And because we can't take 0 dB as SNR value, we need another number basically, and that's 30 at that stage for this transceiver. Okay, that's it for the test at the moment. Going back to my presentation, I'm pretty much through, and I want to summarize it a little bit, what we figured out during our test and analysis. The bit error rate in general, when we look at direct detection transceivers, so the ones you operate in your network, we call them also gray transceivers. The typical LRs, ERs, they both have an influence, or they both depend on the temperature changes and the rising temperature and the fiber length. So it does a direct influence on the bit error rate. As I showed, the bit error rate is a rolling average, so you need to give it a little bit time when you see bit error values to settle it down, a couple of minutes or hours to really have a proper value there in your link. And then the last, or the one I also showed about the temperatures, there is not a lot of margin for those high-speed transceivers when it comes to the high alarm threshold. So when you see a high alarm on your transceiver, most probably soon this link will drop, so you will have a loss anywhere. So when you see a high alarm in your link or in your management interface or on your network management, then you should really look what's the root cause for being on that high temperature. On the coherent side, it looks slightly different. The coherent ones, they really mainly look or are influenced by the length of the fiber, but temperature changes on the they don't influence that much the bit error rate. Basically, within the specifications, for sure. When we are over spec, it will influence it, but it's more the length of the fiber. And the reason is, A coherent transceiver does make use of way more properties of the light. So a gray transceiver, or the direct detection ones, they mainly use the amplitude on our signal. Now a coherent one also makes use of the polarization and the phase. And this makes a way more robust signal at the end of the day, and it's way more capable to correct errors when they occur, because we have way more properties, like I said, the phase of the light or even the polarization. And the good thing, to sum that up, is when you as a network engineer operate a link and you see bit error rate values, you don't have to bother much about the signal to noise ratio, because they are close to each other. They are correlated with each other. So when you have a good BR, the SNR will also be most probably good. So for the moment, you can leave that to the transmission folks. That's basically my summary of the presentation, and I'm happy to take questions, and I'm also going to be around the whole day. Thank you very much.
Okay. Thank you, Mr. Weible. Maybe have some questions. Just raise your hand. Yeah, maybe you will think of something, because we have 2 minutes left, so... Oh, yeah, we have one. Microphone is here.
Hi, I'm Adam. So I noticed that when you speak about the temperature, you always speak about the higher temperatures. So I know that in data center, the problem is always the heat, but not the cold. In my experience, a few years back, we actually had a problem in Texas when there was a huge power outage and everything was too cold. Did you ever had the opportunity to test how the temperature impacts the optics on a lower temperatures when it goes to 0? Thanks.
Very good question, Amanda. Thank you very much. No, we didn't do tests on the lower temperature so far, because from the setup it was way easier to look at a higher temperature at the moment. Because the 0 degree is somehow of interest, but the interesting one is scanning at -20, -30 degrees, and there we faced some challenges to cool it down that heavily, or even down to -40. You basically need something like liquid nitrogen, and at the moment we didn't look into that to cool it down that much, but it's an interesting attempt, and I'm thinking about it. Thank you very much.
Thank you very much. Another one, maybe? And final question for Mr. Weible? I think okay. Okay, so thank you. Thank you once again. It was very detailed.